Dear students, in this video, we are going to see how we can draw the AC equivalent circuit of a common source field effect transistor amplifier. Right? The lecture notes is already shared with you in Google Classroom. Right? Under BJT and FET section, you can find there are 3 documents uploaded in that section. One is lecture notes on BJT, lecture notes on FETs, and the other one is there are a couple of questions on transistors, right? So you can work out on the question based on the lecture notes, and in this video I am going to show you how we can draw the hybrid or the H parameter equivalent circuit or a AC equivalent circuit of a FET based amplifier. First of all, yeah, as we know, this is the circuit symbol of a field effect transistor, right? N-channel field effect transistor, right? This FET, right? The AC equivalent circuit, the derivation is given in the lecture notes, right? Which is not necessary for your exam point of view and solving the circuits, right? So the equivalent circuit could be, right? There is a gate terminal, and this is your source. This will be the gate. Right here, you can see that from the structure, the gate and channel is isolated with the depletion region. Right? Hence, here there is the terminals or the resistance between gate and source. We simply assume it as infinity or as an open circuited terminals. Right? The voltage between these two terminals will be VGS. Right? At the same time, at the output side, we have our current source. Right? This is GM into VGS. Right? The GM is the transconductance. Right? So we can see that the input is voltage and the output is current, what we have. Hence, the VGS has to be converted, right? The voltage has to be converted into current, right? Hence, the GM is called as the transconductance, right? And also, we have a resistance or the channel resistance, right? RD, small r and small d, right? RD. So this is the equivalent circuit of a field effect transistor, right? So this will be your drain terminal. This is your gate terminal. The whole line will be your source terminal. Right, so let's see how we can draw the equivalent circuit of a transistor circuit. Right, first of all, let's consider a common source amplifier, right? A potential divider biased common source amplifier. Right, so here I can have my transistor. Right, so this is your source resistance Rs, and you will have a bypass capacitor, right? And then will be your VD, and this will be your D or drain resistance. Since we are going to have a potential divider bias or simple gate bias, right? So this will be R1 and R2. Here we have the internal resistance of the source, right? Whenever you have a source Vs, that should be Yeah, that with an internal source, let this be RS or the internal source, and this is your ground terminal, and you will have your output cross, yeah, VDS. So this will be your V out. Right, so let's see how we can draw the equivalent circuit of this field effect transistor amplifier circuit. Right, there are three rules you have to follow to draw a hybrid equivalent circuit. Right, step one, you need to short circuit all the DC sources appeared in the circuit or included in the circuit. Right, so step one is short circuit all DC sources. Right here we have VDD as the DC source. What we have to do is we need to short circuit it. We need to ground it. What I can do is I can simply draw a line between VDD and ground, or eventually the VDD is short circuited. Right? Step two is short circuit all the capacitors. Right, short circuit all the capacitors. Or yeah, of course, you may have an input filtering capacitor here and an output filtering capacitor at this point. Right, so rule number two or step two says short circuit all the capacitors including this one. Right, so here an interesting thing is when you short circuit this capacitor, obviously the RS will be simply removed from the circuit, right? Which means you are making a zero parallel path, right? So 0 ohm parallel RS, which becomes 0 ohm, right? So RS parallel 0 ohm becomes, so RS will be short circuited by this bypass path, right? And then finally, the step number three is redraw this, right? Step number three is, right, substitute the equivalent circuit. Right, so this is the equivalent circuit, right? So you have your ground, so this is your ground terminal, this is your drain, and this is your source terminal. What you have to do is you have to fit this circuit in between these two lines, right? In between, within these 3 points, right? I'll show you how we can draw the circuit, right? So simply, yeah, I'll use, yeah, I'll draw the circuit again, right? So, right, so now we know the equivalent circuit of a BJT, right? So, this is gate, and this is your, right, this is your gate, this is your source, TM into VDS, you have your small r right? And just refer the circuit in this diagram, right? So now what we are going to do is we are going to draw the equivalent circuit, or we are going to complete the whole circuit, right? So what we can do here is, right, you can see that this is your gate terminal, right? This is your gate terminal where you have your gate, right? So at gate you have R1 and R2. R2 is connected to the ground. Remember, R2 is connected to ground and not RS, right? So we may have a ground line here, right? So from gate we have R2, right? So connected here. Then from R1 we have our VDD line, which is eventually short circuited, right? Next, we have our RD, right, which is connected to drain terminal, right? This one is your drain terminal and to your VDD, right? So this is your drain. So here you have your RD and this is your grounded VDD line, right? Now, the next thing what you have is, of course, RS or your source terminal is simply short circuited, right? This RS will be removed from the circuit, right? So your source is short circuited by the bypassed line, and then you have your RS and VS in between gate and ground, right? So this is your gate line, this is your ground line. In between your gate and ground, you have your RS and VS. Right now, this is your equivalent circuit. Right. So now, right. Look at here. So where is your V out? Right. Where is your V out? Is across your drain terminal and the ground, right? So your V out is in between your drain and ground, right? So this is your V out, right? So this is your VS, this is your V out. Now you have completed the circuit with the equivalent circuit of a field effect transistor. Right now, this is the equivalent circuit of a field effect transistor. Now let's see, right? So now this line is your ground line, right? So the voltage at this point is 0, 0, 0, 0, 0, 0, here 0, 0, 0, right? Because all these lines are short circuited, right? We know that connecting equipotential lines in a circuit does not going to make any changes in your electrical circuit, right? For example, the voltage at this point is 0, this is R1. What I can do is I can simply pull this off and I can connect it here, right? So this will become, right? So what I can do is I'm pulling this off from the circuit and R1. Right now, these R1 and R2 become parallel. Right? Again, see, look at these lines. What I can do is I can simply pull this line to the ground, right? What I can do is I can simply remove this one and I can connect these lines directly to the ground, right? Which is not going to make any huge change, right? So these lines will not be there in your final circuit because the whole line has ground. Right, again, yeah, we can remove this one and you have your RD. Right, this is 0 and this is 0. I can simply bring this RD across this one, right? So I can pull this off and connect it to here. So I can draw your RD somewhere here. RD. And then this will be removed from your circuit. Right, the whole thing will be removed. Right, now I have a circuit, right? I have an equivalent circuit, which is only this one, right? So now what you have is, you have a VS, RS, R1 parallel R2, and then Gm into VGS RD along with this capital RD. Okay, I'll redraw the circuit, right? I'll redraw the circuit without the marks. Yeah. So what I can do is, of course, here I will have my RS, VS, and then, of course, I can join R1 parallel, R2 together. This is my gate, and this is my line. The voltage between these 2 points are VGS, right? The voltage between these 2 points are VGS, right? Again, I have my current source here, which is Gm into VGS, right? Parallel for R, T, and of course I have another capital R, T, and the voltage across these 2 points will be my V out. Right, so now this is the final equivalent circuit of your common source amplifier, right? Common source field effect transistor amplifier. Now we can simply solve the current gain, voltage gain, and the other parameters of this amplifier, right? Right, usually, right, the RS will be in terms of 50 ohm, 50 to 100 ohm, right? The internal resistance of the voltage source will be much less than your R1 parallel R2 value, right? What you can do is you can simply neglect this one, right? Whenever you have a small resistance parallel to a very high resistance, you can simply neglect the very high resistance. And again, you have RD parallel RD, right? We may have them as a single resistance, right? Hence, now the circuit can be further simplified as, right now, RS, VS, right? So this is your gate, and this is your VGS, Gm into VGS, right? And parallel to these two resistors, right? One is RD and the other one is capital R, right? So this is your, right, let's take it as Z, right? Which is equal to RD parallel RD, right? Or in simple words, Z equals RD into RD over RD plus RD, right? And the voltage between these 2 points will be V out, right? I can draw that one. So the voltage between, or the voltage across the resistance Z will be your V out, right? So now you can see that the current through the field effect transistor amplifier is Gm into VGS. Let's assume that the current through the resistance Z equals I, right? The resistance through the current equals I. Right now, you can simply write your V out as, right, I into Z. And from this, you can see that you have only one more current source, right, which is in the opposite direction. So you can write that I equals minus Gm into VGS. So now you can write your V out as minus Gm into VGS into Z. Right? Similarly, let's see how we can solve for the other ones. Right? So, of course, you can see this one, right? So, if I have the current I, or if I want to mark it in this figure, this is your current I, and the current through RD will be I out. Right? The current through RD will be I out, which means simply the current I will be divided along these two resistance, right? Based on RD and R, small rd and capital RD. Right? Now, your V out, you can see that you have written that V out equals minus Gm into VGS into Z. Look at this figure. What is your VGS? Right? You can see that the gate source terminal, right? This part of the circuit is open circuited. Hence, you are not going to have any current through the loop, right? So, if this is Vs, since there is no current, the voltage drop across Rs will be 0, right? Hence, your VGS will be simply equal to Vs. So, we can write it as, right, here, V out equals minus Gm into Vs into Z, right? So, V out over Vs equals minus Gm into Z, right? So, V out over Vs will be your voltage gain, right? V equals minus Gm into Z is this one, right? So, Gm into RD into RD over RD plus RD, right? So, this will be your voltage gain of a field effect transistor amplifier. Right? Again, from the circuit, you can see that the input impedance of a field effect transistor is infinity, right? Since the gate terminal is open, so you may assume that the input impedance of this amplifier, this particular amplifier, is infinity, and the output impedance is directly Z, right? So you can see that the voltage gain of the field effect transistor amplifier is minus Gm into RD over RD, RD into RD over RD plus RD, where Gm is the transconductance of your field effect your FET. Right, and this minus indicates the phase shift, right? The 180-degree phase shift induced by the or produced by the field effect transistor amplifiers, right? So we can do a couple of examples now, right? So this is how working out on a field effect transistor circuit, and now in our next video I'll post how we can use this one to solve a couple of examples.